class on fundamentals of electrical engineering. We had moved into the second module where we were discussing the electrical machines. After completing DC machines, both motors and generators, we moved into transformers, and then we had the induction machines. The first section generally talked about general aspects as also the speed as also the torque. And in the second section on induction machines, we also discussed the starters, a very essential component of the induction motor, such that the best of torque with respect to the starting current can be achieved. Now we go on to the most widely used kind of induction machine, that is the single phase motor. There are different types of single phase motors. We're not going to the theoretical aspects of them, but some of the problems that have come in gate examinations, which will perhaps reveal the fundamentals to you in all its strength. So let's look at the first question. The direction of rotation of a single phase capacitor run induction motor is reversed by. Okay, so the first idea that comes to our mind is to, of course, the first answer, interchange the terminals of the AC supply. But just let us look at the other answers, which are not the correct options. One is, of course, interchanging the terminals of the capacitor. The capacitor behaves to an AC in a similar manner, whatever be the phase or the neutral of the supply. Similarly, interchanging the terminals of the auxiliary winding also will not change the direction of rotation of the single phase induction motor, capacitor on induction motor. The fourth option, interchanging the terminals of both the windings, is also just not going to work, because now since the forward and the reversing torques are still not are in the same direction, so we have what is called as the machine running in the same direction. The only thing that will work will be the interchanging the terminals of the AC supply such that the phase and neutral get altered. Moving to the next question. Starting torque can be obtained in the case of a single-phase induction motor with identical main and auxiliary windings by connecting. So we have a problem in the sense that when there are identical main and auxiliary windings, they both have the same torque, or the forward and reversing torque happen to be the same. So now to have a difference, a phase difference between the two, there are several techniques. Okay, so, and let's see, and what is and of the several techniques given, one is the best, and that's what we are going to pick up. The starting torque can be obtained in the case of a single phase. Okay. A capacitor across the mains does not help. It just improves the power factor. The capacitor in series with the machine also does not help, because it's just again a sort of a it is again a sort of a filter. Okay, the capacitor in series with the auxiliary winding, yes, exactly. This is the exact way of getting a good starting torque, such that the forward torque is bigger than or larger than the reversing torque. This is the method, and so the machine starts. The main putting the main and auxiliary windings in series does not work. I hope the option is clear to you. So now let's look at the third problem. In the third problem, it is easily recognizable or diagnosable as the equivalent circuit of a single phase induction motor. Can we work on single phase induction motors? There are two circuits in series with respect to each other, and there is of course there is R1 and JLX1. So R1 and JLX1 refer to the stator, that is the main winding. Okay, and then we also have two circuits which are in series with respect to each other, which are referring to the rotor part of the circuit. Okay, so the rotor part of the circuit will produce both the forward torque as also the reversing torque. Okay, so it is ultimately the forward torque that prevails, and so we see that when S is equal to near around 0, which is what we call as the no load speed, then we see that the top winding opens out, because when S is equal to 0, so then we have only the magnetizing winding working. Okay, so that's one circuit. In the next circuit, when S is near around 0, then we are having R2' by 4. Okay, so that's this is the difference between the two circuits. On the other hand, when S is equal to 1, that is at starting, in winding number 1, we are having R2' by 2 as the effective resistance, and winding number 2 is a difference in the resistive component, both at starting as also during when the machine approaches the almost the full load, okay, or no load speed, okay, or slip as equal to very very small, okay. So now so I suppose the circuit diagram is clear. We also have JXM by 2, or the magnetizing reactance, split into 2 and in parallel with the combinations of R2 dash by 2s in series with JLXXL2 dash by 2, where XL2 dash refers to the leakage reactance of the rotor referred to the stator. The dash refers to the stator. Okay, so similarly we have a similar content in the circuit down below as well. Okay, so this is the circuit, and a voltage is applied and it's taken as reference, so we mark it out as equal to angle 0 degrees. Okay, so let's read the problem and see what is required out of us. Okay, so though the circuit looks a little complex, of course it's a well recognized circuit. At the same time, the method, the what is required out of us should be very very simple. This is the standard nature of gate questions. Okay, the equivalent circuit of a single phase induction motor is shown in the figure, where the parameters are R1, R2 dash, R1 equal to R2 dash, equal to XL1, equal to XL2 dash, equal to 12 ohms. Okay, so all these values are 12 ohms. As I said earlier, the problems are generally very simple. Okay, and XM is the only large one, which is equal to 240 m. Okay, 240 ohms, and S is the slip. Okay, at no load, okay, and when S is near around 0, the motor speed can be approximated to the synchronous speed. As is why we say that S is equal to 0, near around 0. No load lagging power factor of the motor is what? Okay, so power factor is asked at no load. So at no load, S is equal to, as I said earlier, S can be equated to 0. So in the top circuit, we notice that the resistive branch opens out. Okay, and in the bottom circuit, in the two series circuits for the rotor, we see that we have R2 dash as we have the resistance equal to R2 dash by 4. Okay, so now it's a very simple circuit. Okay, and so and the power factor is asked, so we can pick up the resistances and the reactances and get their ratio to obtain the power factor angle. So what do we have? We have R1. Okay, so let's go via the circuit, picking up the resistances just like as a current would do. So R1 is equal to 12, and then we are having nothing in the top parallel circuit, because it's simply JXM by 2, because R2 dash by 2S, where S is equal to 0, has opened out. Okay, and then in the bottom circuit we are having JXM2 parallel to R2 dash by 4, that is 12 by 4, that is 3, and then again we have JXL2. So now we have an understanding about the resistances. Okay, but at the same time, JXM by 2, which is 120, that is 240 by 2, which is J120, is parallel to a circuit which has R2 dash by 4, which is 3 ohms, and then JXL2 dash by 2, which is equal to J6. Okay, so 3 plus J6. Okay, 3 plus J6 is parallel to J120. So what does it mean? It means that the parallel combination has an impedance which is less than 3 plus J6. So we can as well take 3 plus J6 and avoid JXM by 2. So in effect, what has happened is that the one of the parallel circuits in the top circuit, wherein R2 dash was present, is absent, and in the bottom circuit, JXM by 2 is absent, or it's opened out. Why? Because it is parallel to a very small impedance branch having 3 plus J4 as its constituents. So now it's very simple to see that now we are having a series circuit. So we pick up R1 and R2 dash by 4. Okay, so that's equal to so that's equal to 12 plus 3, 15 ohms. Okay, and then we pick up all the reactances. We have JXL1, which is 12, and then we are having JXM by 2 because its alternate circuit is open. So we have 120, and then we see that JXM by 2 in the bottom branch is open. So we have only JXL dash by 2, which is equal to another 6 ohms. So now in total we are having X is equal to 138. Okay, so R is equal to 15 and X is equal to 138 gives us a power factor as given by cosine of tan inverse 138 by 15, which is as small as about 0.104. Okay, the answer given in the answer that is, okay, of course you can find out the answer. You can see that it's between 0.104 to 0.112, as is normally given as the guidelines in GATE examination keys. Okay, so I suppose this is also a very simple problem. So long as you understand that there is only one important thing, that at no load, slip is equal to 0. Okay, so slip is near around 0. Second is, of course, in a parallel branch, whenever we are having an impedance which is much smaller than the larger impedance, then the impedance is going to be a little smaller than the smaller branch. So we need to retain only the branch with the smaller impedance. Okay, so let's move to the next problem or the next question, which tells us that a 230 volt 50 hertz 4-pole single phase induction motor is rotating in the clockwise or forward direction at a speed of 1425 rpm. Okay, so we know how to calculate the slip here. Now we know how to calculate the synchronous speed here. Same old idea of 120 F by P, and slip is also there. If the rotor resistance at standstill is 7.8 ohms, okay, so R2 dash at S equal to 1 is given as equal to 7.8. Okay, so now we know that. Okay, so we know the two resistors. Okay, then the effective rotor resistance in the backward branch. Okay, so the backward branch was the bottom one, and that was given by 7.8 by 2. Okay, so near around 4 ohms. That's all that's required. Okay, so a simple remembrance of the equivalent circuit wherein we had R2 dash by 2 S, okay, yeah, and also R2 dash by 2 into 2 minus S. Okay, so here we see that we have half the resistance is now being employed in the backward branch. Okay, so now let's go to the fifth problem. In a single phase induction motor driving a fan load, the reason for having a high resistance rotor is to, okay, so we notice that the resistance in the rotor is normally high both for single phase and three phase induction motor. This gives rise to a big acceleration, okay, a quick acceleration, which is what is required in a fan load. Okay, and from the different options, one is of course low starting torque. Okay, of course nobody tries to obtain the low starting torque because the machine has to start from rest. High efficiency, when you increase the resistance, there is no way of getting a high efficiency. Reduced size is also not possible so long as you increase the size of resistors, inductors or capacitors. Okay, so we move to the sixth problem. A single phase induction motor with only the main winding excited would exhibit the following response at synchronous speed. So main winding is what is giving the forward torque. So of course because the auxiliary winding gets cut off, and so it's only the main winding which is going to remain. So it is always associated with the forward torque. Okay? So rotor current is 0, rotor current is non-zero. So from the different options, rotor current is 0, rotor current is non-zero, and is at slip frequency. Forward and backward rotating torques fields are equal. No, none of this apply because only auxiliary winding, only the main winding is excited. Okay, so forward rotating field is more than the backward rotating field. Okay, so that's the correct answer, and we opt for that. Okay, so now the next 7th problem looks a little more complex, but don't worry. Let's see if we can do it in a very simple manner. Okay. There's a formula, but at the same time, what it means is going to be very, very important. Okay, so a 375 watt, 230 volt, 50 hertz capacitor start single phase induction motor has the following constants for the main and auxiliary windings at starting. So all these values are given at S is equal to 1. Okay, Zm, that is the main winding, as we saw in the earlier case. In the equivalent circuit, it's given by 12.5 ohms as the rotor resistance, and J 15.75 as the reactance, okay, leakage reactance. Okay, so this is for the main winding. Okay, and for the second winding, the auxiliary winding has 24.5 as the resistance. Okay, and then the reactance component is 12.75. Both are smaller. Okay, auxiliary winding. Neglecting the magnetizing branch, the value of the capacitance in microfarad to be added in series with the auxiliary winding to obtain maximum torque at starting. So the general way of starting the machine is now given as a problem, in the sense that the auxiliary winding will have a capacitor such that there is a 90 degrees phase difference, near around 90 degrees phase difference between the two, okay, which will actually give you a forward torque which is bigger than the reversing torque. Okay. Now here we have another important issue, so please be careful about that. It said that that the maximum torque should be obtained at starting, which is a little different from the earlier case. Okay, so here we have another condition as well included in the problem, that there is a maximum torque which happens to be at the starting itself. Okay, so now a small vector diagram is given right beside such that this formula can be explained. And there's a formula which we will be utilizing. Okay, so we have what is called as the auxiliary, the main winding, just put with an angle of with a lagging angle, because it's an inductive coil. So main winding is given as shown there with an angle phi m. Okay, and then we have to have the auxiliary winding such that it makes another angle, because we are putting a capacitor there, and that capacitor will give rise to a leading for the angle, lead angle for the auxiliary winding, such that we achieve phi a. And so it is clear that we have the remaining of the remaining in the first, the remaining angle in the first quadrant should be 90 minus phi a. Or in other words, the requirement for getting the maximum torque, okay, that's possible only when you are having the current and the flux at 90 degrees, exactly at 90 degrees with respect to each other. Okay, so it's obvious that 90 minus phi a should be equal to phi m plus phi a. Okay, so both the angles together should match 90 minus phi a, or in other words, 90 should be equal to phi m plus 2 phi a. Okay, so if you 90 minus phi a, if it's equal to phi m plus phi a, it means that 90 degrees should be created out of phi m plus 2 phi a. Okay, so phi m is the angle of the main winding, which can be obtained by tan inverse 15.75 by 12.5, and phi a can be obtained by again another tan inverse of 12.75 by 24.5. But of course, we also have a capacitance, so xc minus 12.75, that is going to be the inductive component or the reactive component there, divided by 24.5 should be equal to 90 degrees. So only one unknown is there, which is xc, which can be found out as equal to 149.5. xc can be obtained, and it's a 50 hertz machine, so we can have omega is equal to 314. So you put them all together and you see that C is equal to 149.5 microfarad as is obtained. Okay, so I repeat the vector diagram again here. So to get the starting torque as the maximum torque, the relation that comes out is that you have to put in xc such that there is an angle of lead. Okay, and together they should be the angle should be such that phi a plus phi a is equal to 90 minus phi a. Okay, I hope this is clear. Okay, yeah, phi m plus phi a is equal to phi m plus phi a should be equal to 90 minus phi a, or 90 is equal to phi a plus 2 phi a. Okay, so these are the angles of the main and auxiliary winding. So you can find them out, and you can see that phi a is created out of xc minus 12.75. Why minus? Why? Because the capacitive reactance is positive, whereas the inductive reactance is considered negative. Okay, so as simple as that. Okay. Yeah, so moving on to the 8th problem, which is again a single phase induction motor, a single phase 230 volt, 50 hertz, 4 poles, capacitor start induction motor, just as before, has the following standstill impedances. Okay, in the early case also it was standstill impedances. Mean winding is given by Zm is equal to 6 plus J4. Okay, so we have both the resistance and the reactances for the main winding, as also for the auxiliary winding, as Za is equal to 8 plus J6. Okay, so now we can calculate both phi m as also phi a. Okay, the value of the starting capacitor required to produce 90 degrees phase difference between the currents in the main and auxiliary winding. So in this case, they are not talking about the maximum torque being available at starting. Okay, or in other words, we can just simply find out the angles between them, and such that the capacitor is also added, and then the angle should be the angle between them should be equal to 90 degrees. So there are two different cases. Please understand that there are two different cases. One is where the starting torque has to be obtained at has to be the maximum torque. In this case, the angle has to be 90 degrees. Directly, the angle has to be 90 degrees between them. So we see that we are having angle of the auxiliary winding as equal to tan inverse. The angle of the main winding is given by tan inverse. It is in the auxiliary winding that we are putting the capacitor. So we find out the angle of the main winding first. Tan inverse 4 by 6, which is equal to 33.69. So the angle of the auxiliary winding has to be 90 minus this, which is equal to 56.31. So, and what is the angle of the auxiliary winding? It's given by tan inverse of x by r, or where x is equal to xc minus 6. Okay, so tan 56.31 is equal to 1.5 is equal to xc minus 6 divided by 8. Okay, where 8 is the resistance and 6 is the reactance of the auxiliary circuit, which has not obtained the capacitor as such. Okay, as such, once the capacitor is obtained, the reactance becomes xc minus 6. Okay, so now it's very simple to solve it, and you see that xc is equal to 18, and it's equal to 1 by omega c. So omega is 314, and so c is equal to 176.9. So subtle differences between the two, I suppose it's well understood. Okay, so now we move to the ninth problem. The question: the type of single phase induction motor having the highest power factor at full load. Okay, so when the machine is at full load, what is possible is that we are having inductive reactances only. So if you are having a capacitor during the running time as well, then that machine is going to have a high power factor. Okay, so of the shaded pole is just it's not right. Split phase is also not right. Capacitor start provides a high power factor only at the starting case, but capacitor run is the capacitor is available even during the running of the machine. So, and that's when the full load occurs. So at full load, the best option is to go for the capacitor run motor. Okay, so now we come to the last of the problems in this session. What do we have here? We have 220 volt supply being given via a switch to two coils. The first coil is having RA as 1 ohm and LA as 10 by pi Henry, and then the second coil is having RM and LM as, respectively as 0.1 ohm and 0.1 pi Henry. Okay, 0.1 by pi Henry. Okay, and we are having the first coil is A1 A2. That is one winding, and M dash is another winding. So main and auxiliary winding, obviously main and auxiliary winding. One is M dash is the main winding with resistance reactance combination as 0.1 and 0.1 by pi Henry. Okay, and A dash, the auxiliary winding. Okay, it doesn't seem to have a reactance. No, a capacitor still has only RA and RA equal to 1 ohm and LA is equal to 10 by pi Henry. Okay, and what is asked? So let's see, 220 volt 50 hertz is applied. Okay, I suppose the diagram is clear. Now a 200 volt 50 hertz single phase induction motor has the following connection diagram and winding orientation shown. M dash is the axis of the main stator winding, and A dash is that of the auxiliary winding. Okay, directions of winding axis indicate direction of the flux when currents in the windings are in the direction shown. Okay, so if the currents are shown in the direction which are also shown there, then we are having 90 degrees phase difference between them. Okay, the parameters of each winding are indicated. When switch S is closed, the motor, okay, what happens? Okay, so does it rotate clockwise or does it rotate anti-clockwise, or it does not rotate or rotates momentarily and comes to a halt? Okay, so what happens? Okay, so obviously both the windings have both the windings are connected exactly across the same supply. Okay, so what happens is that both are inductive. Okay, and there's no capacitance at all. So of course there is no phase difference, and because they have the same, and just let us have a look at the angle. The tan phi A is the tan phi A is 10 pi Henry 10 by pi divided by 1. Okay, or it is equal to 10 by pi. Okay, and tan phi M, or the angle. So the main winding, it will be given by, or the tan value will be given by omega. Of course, omega is the same. Okay, omega 0.1 by pi divided by 0.1. Okay, so it seems both the angles are the same, so they will not have a phase difference. If they do not have a phase difference, you will not have what is called as a rotating you will not have rotation, because forward torque will not be equal to rotating. It will not be larger than the reversing torque. I hope the general ideas in the single phase induction motor are very clear to you. The main objective is always to have a forward torque larger than the reversing torque, and for that we introduce the capacitor. There are two ways of introducing the capacitor. One is by seeing that the maximum torque is available at the starting itself. In that case, we see that 90 degrees should be equal to phi m plus 2 phi a. On the other hand, you can always have 90 degrees between them, okay, by introducing a capacitor again. But then we just look at the angle between them. And in this case, in the last problem also, we had we can find out the angle by finding the tan inverse of omega L m divided by omega by Rm when compared to omega L A auxiliary winding divided by RA. Okay, so when these both angles are compared, you can see if there is an angle of near around 90 degrees, then you can, if the angle is perfectly 90 degrees, then you can have maximum torque. Okay, otherwise, if there is an angle between them, you can definitely have a forward torque which is larger than the backward torque, and the machine rotates. Okay, I suppose the different aspects of problems that may come in gate context are clear to you. Please remember the relevance of the single phase equivalent, the equivalent circuit of the single phase induction motor, wherein we are having two windings opposing each other, such that the one, of course, the one that provides the backward torque or the auxiliary winding opens out, and the main winding remains, and the main winding remains because it is creating the forward torque. Okay, the reversing torque is created by the combination, but then what is done is that the auxiliary winding is switched off after some time. So the best kind of motor is always going to be the capacitor run, capacitor start, capacitor run motor, such that we are having a better power factor as well. Okay, so I suppose what is more or less fundamental to single phase induction motor are more or less covered in this session, and you'll be able to any problems in this session as well. Thank you.